Hello, welcome to Chapter 4, Material Science and Engineering. And the last time we talked about imperfections in solids, we talked about vacancies, self-interstitials, we talked about impurities in solid materials, and we went further, we talked about specification of compositions, how we can specify these compositions in alloys, and we talked about how these compositions are in terms of atomic percent and in terms of weight percent. And then today what we're going to look at, dislocations and linear defect. And what are dislocations and how can we detect dislocations within materials? So dislocations varies from material to material. We can see that in the next. Okay, these are, you can see dislocations, linear defect. So we have three types of dislocations. We have what we call edge dislocations, we have what we call screw dislocations, and we have mixed dislocation. So when we talk about edge dislocation, you can see here is the atomic structure. In the atomic structure, we have the atoms. The atoms, we have a linear dislocation here at the center of the crystal structure. So within the center of the crystal structure, there is a dislocation here. So when there is a dislocation at the center, then we say that there is a linear or edge dislocation. Okay, but this dislocation we tend to move from one stage to the next. So, but however, if you look at here, we have what we call also the other type of dislocation, which is the screw dislocation. The screw dislocation will be something like a helical within the plane. So that's exactly what we will see. We'll see an example of that now. Okay, so for the screw dislocations, we're going to look at the Burger's vector. So the Burger's vector is the angle within the dislocation, wherein we can use that angle to determine whether this is a mixed dislocation or a screw dislocation or an edge dislocation. So sometimes, again, these dislocations can be parallel or perpendicular. So when it is perpendicular, we say the Burger's vector is parallel for screw. That means it's going with the angle to which the dislocation is going. And when it is perpendicular, it means that if the dislocation is going this way, the angle is going the other way. And for the dislocation, for the linear defect, for the mixed defect, it's neither perpendicular nor parallel. Okay, then we move to the interfacial defect. For interfacial defect, we have what we call external surfaces, we have grain boundaries, we have phase boundaries, and twin boundaries. We have the bulk vectors and atomic vibrations. So when we talk about the external surface, so within the surface of a material, we can see that with our naked eyes. But however, like screw dislocations and edge dislocations, this type of dislocations, we have to use microscope to look at these dislocations and for us to be able to identify which dislocation is which. But for the external surface, we can see it with our naked eyes. However, for grains or grain boundaries, okay, there are also dislocation within grains. Previously, in our previous discussions, we talked about grains and grain boundaries. And also for the phases, within the phases of in this we're going to see phases of materials in chapter 9, where we can talk a lot about phases. Then we can also see dislocations within the phases of the boundaries. And we also have what we call twin boundaries. This is just like human beings. Okay, human beings also, we also have twins. Alright, and the same thing happens in materials. In materials also, there is what we call twin boundaries. In twin boundary is that the dislocation in one side of the material and the other side, they look like the same. Okay, just that they are in opposite direction. Okay, we can take it, I'll come to a typical example of that. So somebody will ask, why do we need to study this? Why do we need to take a lot of time understanding how atoms are arranged within the material? So that will bring us to here. Where do we use this atomic defect and dislocations? For example, if you have a car, we know that the car emits some gases, okay? We have the gas emission, and now we're talking about climate change. We have all these problems within the climate. So if you are able to understand this atomic defect, we can able to arrange these atoms and this mixing of the ceramic materials that are constructed. So we can use cerium, zirconium, and oxygen. We can make a material based on these elements. And then these ones will help to reduce the climate change, because what will happen is that when the toxic gases like carbon monoxide, which is a poisonous gas, when it comes through this material, what will happen is that the carbons will disintegrate here with the oxygen. So, but this is a catalytic converter. If you look at my previous videos, I make mention of the catalytic converter. So you can see the atoms will undergo a chemical reaction, and then upon the exhaust pipe, what you will see is that the poisonous gases will disintegrate within this catalytic converter. So that's why it is important for us to study dislocations in materials, and also in our mobile phones, okay, in computers. Okay, we use semiconducting materials. So it is important for us to understand how the atomic structures and how this operate. Then we use mobile phones in our everyday life. We use computers nowadays. But this is exactly what is happening, because understanding atomic dislocations in materials, we can able to create some silicon that is free from these dislocations, or we can concentrate, we can determine exactly where these dislocations and these atomic defects should be. So that way we can make mobile phones, for example. We can make computers, for example. So this is the reasons why we should understand these defects. All right, and finally, bulk vectors and atomic vibrations. How atoms behave. Atoms, you see here, we make them as like this, but these are vibrating, okay? So when we talk about temperatures of atoms or temperature of a material, even we human beings, why do we feel cold or we feel hot? It's as a result of the movement of the atoms within our body, okay? So the more the vibrations of the atoms, the more the temperature goes up, okay? So if we increase this temperature as well, the vibration of this also will increase. So atoms can also move in the form of bulk, okay, as groups. So that's why we have also the bulk or volume defect, these things. And then we move to the microscopic technique. So these things, you cannot see them with your naked eyes. You have to use microscope. And so we have different type of microscope. We have the optical microscope, we have the electron microscope, and the scanning probe microscope. So these are different types of microscope that see. For example, if you want to see an atom, we talk about atom every day, but how can you see and taste the atom? So you have to use what we call the recent one, the electron microscope, because this one will help you to see the atoms. But if you want to see just the dislocations, you have to use the optical microscope, and we can explain these techniques, how these microscopes work. Or if you have also the scanning probe microscope. So because we cannot see this with our naked eyes, we have to go down deeper to look at this. So we create microscope to be able to study this. And finally, in this chapter, we're going to see the grain size determination. How can we determine grain size? Okay? And these intercept methods, they are mathematical calculations in which we can use to determine the grain sizes, but we have to understand how the microscope operates. And if you follow my lectures, you can understand how the microscope techniques and how we can build a microscope by understanding these things. So today, we come to the end of chapter 4. So next, in my next video, we're going to start chapter 5, which we're going to continue again with diffusion. Diffusion is how atoms move within a material. And that is so important because for our mobile phones, for our computers, how these atoms move, how we play games in our computer, all this is possible because of understanding the atomic structure. Why today we can communicate, why are you seeing me right now when I'm talking? All this is understanding these techniques and the diffusions of materials. So until then, have a great day. Goodbye.